Started now. So hi from Canada. I've been here for now about little more than 24 hours, and weather's pretty good actually. And well, anyway, so today actually I went to get my driving license, and I it was a simple procedure. So they asked me my height, my weight. I told them, and then the eye color. That too I told them. And then the lady at the counter, she said hair color. She said black, and then looked at me. And we started laughing. Well, anyway, so that's what happened today. So anyway, I got the license. So now I'm free to drive. So, I mean, having a car here is a big deal. So, all right. So getting to the topic now. Raish, can you please put your mic on mute? Okay. Thank you. Still not muted. Oh, yeah. Now it's muted. Okay. Thanks. So what we'll talk about today is flow across hydraulic conductivity boundary, right? So we were talking about flow nets, the idea of flow nets and so on. So what happens when flow approaches a boundary where two different hydraulic conductivities meet? Okay, so I have a conceptual picture over here. Okay, so I have a dividing line somewhere here which divides these two different hydraulic conductivities K1 and K2. Let's not worry about which one is greater or smaller at this point in time. And let us say the flow is approaching this boundary at some arbitrary angle theta 1. Okay, theta 1 with respect to the vertical. Okay, so I have this vertical line here, and the flow is approaching the boundary between K1 and K2 at an angle theta 1 with respect to the vertical. And then once it crosses from the region K1 to the new region K2, the flow is actually getting diverted or deflected at an angle, let's say theta 2. Okay, so that's what is happening here in this particular instance, where I have these two zones with two different hydraulic conductivities, K1 and K2. Now, the way I've drawn this conceptual picture, the dotted lines are the equipotential lines. Okay, there's multiple dotted lines. Maybe I'll rephrase that. Let's try changing the color of the ink. Okay, we'll make it blue. That might be better. Okay, so this dotted line, okay, is an equipotential line. Okay, and I have another dotted line here, which is another equipotential line. All right, and the solid lines with the arrows represent the flow lines, which by definition will always be orthogonal to the equipotential lines. Now, the angle made in zone K1, where the hydraulic conductivity is K1, the angle made with respect to the vertical is theta 1, and in the second zone, where the hydraulic conductivity is K2, the angle made with respect to the vertical is theta 2, but the angle made with the respective equipotential lines is still 90 degrees in both these zones. Okay, at the interface, the equipotential lines actually change direction, right? So you can notice that in K1, the equipotential lines are at a particular angle, and in K2, the equipotential lines are at a different angle with respect to that interface line, the horizontal line. Okay, so this is the flow that's coming in. So if you take any two particular flow lines, okay, the flow coming between those two flow lines cannot change. Remember this idea, because a flow line by definition is a no flow boundary. No flow can go across a streamline. right? So whenever you see a streamline, you have to get this idea clear that a streamline is a no flow boundary, because no flow can go across a streamline. Okay, you can think about it mathematically, you can think about it physically, whichever way you think about it, there can be no flow cutting across a streamline, which means that the flow coming between, let's call this streamline 1 and streamline 2, right? So streamline 1 comes in here at an angle theta 1 and then gets deflected at an angle theta 2 and goes this way. So this is the incoming 1 is still going out here 1, and the incoming 2 is going out here as streamline number 2. What I'm trying to say is that the flow coming in between streamline 1 and 2 in the K1 region will be the same as the flow going out between these two streamlines 1 and 2 in region 2. Okay, so now how do I find the flow rate between any two streamlines? So the flow rate between streamline 1 and 2 will be K times the hydraulic gradient times the area across which this flow is happening, right? So if the Q between these two lines is constant, how do I find the Q? It is K times I times A, right? This we've already learned in Darcy's law, right? So we have K1 times I, the gradient in region 1, which I'm calling it dH1 by dL1. That's the gradient. Now dL1 is the distance between the two equipotential lines. Over here I've marked dL1. It is this distance, and the head difference between these two these two equipotential lines is H1 and H1 minus dH1. Okay, head is declining, so at this equipotential line has got a head of H1, let's say. The second equipotential line has a head of H1 minus dH1. By that much the head is declining. Okay, I've skipped a step here, I'm sorry about that. So times the area through which the flow is happening, so that would be AB times cos theta 1. So I should write AB over here, multiplied by cos theta 1, multiplied by some unit thickness perpendicular to the screen. That would give me the area through which the flow is coming, right? So the flow K times I times A. Now that area is AB times cos theta 1 times some unit thickness perpendicular to the screen. Okay, so that AB remains there. Now coming to the second region, it's again K, but now it's K2 because the hydraulic conductivity has changed. K2 times dH2 divided by dL2. Now dL2 is this distance between the same two equipotential lines, and let us assume that those equipotential lines are given by H2 and H2 minus dH2. So the head difference is dH2. So I write that over here, dH2 divided by dL2, that's the head gradient, multiplied by AB. This same AB cos theta 2 will give me this distance, right? If this is theta 2, then this will be 90 minus theta 2, right? So sine of 90 minus theta 2 will be this distance divided by the hypotenuse, which is AB. AB is, point A is over here, point B is over here. Okay, I hope that's making sense. AB is that common interface between.
Sir,
Yes.
sir, the soil is isotropic or anisotropic? Here medium change from K1 to K2. That
Yeah.
means the soil is isotropic or
Wait.
same soil.
In region K1 it is isotropic, in region K2 it is isotropic, but there is a boundary between these two different soils, but the flow is happening through the same uh, uh, flow is happening through these two soils. Okay,
Yes, sir. Yes, sir.
all right. So these things happen in many practical scenarios. You have two different domains with different hydraulic conductivities adjacent to each other, and flow happens to go through both of them. And when that happens, we are trying to understand how it's going to behave. Okay. So any issues with this with the equation that I've written so far? It's K I A. The area is AB times cos theta 1 for the first part, multiplied by some unit thickness, and the area for the second one would be K times I, which is K2 times dH2 by dL2 times AB into cos theta 2, which would be this this distance. This distance is this AB into cos theta 2. Okay, this AB into cos theta 1 is this distance. Okay, cos theta 1 is adjacent side by hypotenuse. This is 90 degrees, remember. So AB is the hypotenuse. So I get that distance by saying AB multiplied by cos theta 1. Similarly, on this side, it will be sine 90 minus theta 2, which is cos theta 2, which will give you AB times cos theta 2 multiplied by the unit thickness perpendicular to the screen. Okay, now AB is there on both sides, it gets cancelled out, and that unit thickness also gets cancelled out. So you're left with this. Okay, so I'll just get rid of this AB over here. Okay, so I'm left with this K1 times dH1 by dL1 into cos theta 1 equal to K2 times dH2 by dL2 times cos theta 2. Now, what can we say about dH1 and dH2? This equipotential line continues here as another equipotential line. Now, if these two equipotential lines, I have denoted them as H1 and H2, but if they meet at this point, at a junction where these two zones are coming in contact with each other, K1 and K2, what can you say about H1 and H2? They must be they must be equal. Is that right? H1 must be the same as H2 because it's the same equipotential line. Those two equipotential lines meet at a point, and by definition, an equipotential line can only have one head, right? So although I written it as H1 and H2, in reality, H1 and
Sir,
H2
it
must
is
be one.
lagging actually. Lagging. Video is
Okay,
lagging.
video is lagging. That's okay, but the question is still the same. H1 and H2, they are both um, meeting at a point, which is the junction between the two zones K1 and K2, right? So can we say that H1 and H2 will be one and the same? Yes, no,
Yes, sir.
right? And if H1 and H2 are one and the same, then H1 minus DH1 will be the same as H2 minus DH2. Yes, they
Yes.
are equipotential lines, which means DH1 and DH2 are one and the same, correct? DH1 must be the same as DH2. The difference in heads between the two equipotential lines in zone 1 must be the same as the difference in heads between the same two equipotential lines in zone 2. Although the distance between them is different, the head difference between them will be the same. Agreed? Yes? No? Okay. So I'll take that as a yes. So H1, DH1 is equal to DH2. So this equation becomes K1, DH1 and DH2 cancel each other out on both sides. K1 times cos theta 1 by DL1 equal to K2 times cos theta times DL2. Cos theta divided by DL2, sorry. Okay. So now what I'm going to do is just a little bit of trigonometry. You don't have to worry about it. So sine theta 1 is DL1 divided by AB and sine theta 2 is DL2 divided by AB. So I rearrange terms a little bit and do some fancy trigonometry. I find then, okay, what's going on? That DL1 sine theta 2 equal to DL2 sine theta 1. Okay, you don't worry about the trigonometry. It's trivial really. You guys can figure it out. It won't take you too much time, right? So I do a little bit of rearrangement and then I find finally what I end up with is something like this. K1 by K2 is equal to tan theta 1 by tan theta 2. This is probably very similar to what you might have studied in what is that, light?
So, sir, soil mechanics, this formula is available.
Okay. No, I'm talking about the the principle. It's similar to light refraction in
Yes, sir. Refraction of light from one
right.
medium to another medium, angle
Yeah,
is changed. Then
yeah.
what is
So
the
you
actually?
would you would get the coefficient of refraction mu one, mu two,
Yes,
whatever
yes.
it is.
Mu one by mu
Right?
two.
Yeah, it would be tan theta, something like tan of the incident angle, if I remember
Ten
correctly.
phi
Something
one
like
by ten phi two.
fair enough. Okay, so this is very similar to that. Now keep that keep that aside. Let us. I'm going to show you two scenarios. I want you to comment on which one is which. Okay, so let us say I have two scenarios here. On the left, I have K1, K2, and then again K1. Okay, and then on the right, I have another series of K1, K2, and K1. And now my question to you is: in one of these cases, K1 is greater than K2, and in one case, K1 is less than K2. Okay, can anybody can anybody figure that out? In which case,
If
if
K1 is greater than K2,
which
then
case?
phi one is less than sorry theta one is less than theta two.
No, no. I want you to think about it from a physical point of view. Take a look at the figure on the left hand side. Okay, can you tell me whether K1 is greater than K2 without getting into the maths? Okay, I know you can figure it out with the maths, but can you figure it out just physically also? Just by looking at it, can you tell me which is greater, K1 or K2?
K1.
K1 is greater. Okay, anybody? Anybody else? Don't look at it. I mean, I'm not saying you can't find out by using that equation given there, tan theta 1, tan theta 2. Suppose you didn't have that equation, could you still figure out which one is greater? Is K1 greater than K2 or is K2 greater than K1? Okay, now think about it physically. Water likes to take the path of least resistance. Yes? So, which means that if the hydraulic conductivity of a particular region is low, then water wants to take the shortest path to get out of that region. Correct? If the hydraulic conductivity of a certain region is low, then water wants to travel the shortest distance possible in that region. It doesn't want to, it will prefer to travel a shorter distance than a longer distance if the hydraulic conductivity of a certain region is low. Do you agree with that? Yes? No?
Yes, sir.
Okay. So, in that case, with that having been said, can you infer from a physical point of view? Shantanu, you've already told us your opinion. Others, can you tell me the figure on the left hand side, which one is greater, K1 or K2? Anybody? You'll have to unmute if you want to speak, or we'll come up with sign language. If K1 is greater than K2, put up your left hand. Raish, what about you? You're not enrolled in the course, but you can also answer. If K1 is greater than K2, you can put up your left hand. Don't want to take a chance, huh? Okay. Well, you can figure it out. That's what I'm saying. The math over there, the equation can help you figure out which of these will be likely. So in this case, in the left hand side, K1 is going to be greater than K2, right? And the exact opposite happens in the other case. K2 is greater than K1. So So that's what of course the equation will also tell you the same thing. You can figure it out either mathematically or physically. So you'll notice here in the on the left hand side, because this zone K2 has got a very low has got a relatively low hydraulic conductivity. Water quickly wants to get out of this. Okay, water wants to take the shortest path. The shortest path by definition is when uh, it takes a perfect 90-degree angle, right? It just goes straight down. That's the shortest path between two straight lines is a 90-degree angle, right? I mean, especially if it's well, anyway, at any given point, the shortest path is 90. The shortest distance is the perpendicular distance, right? It is coming as close as possible to the perpendicular distance because the hydraulic conductivity of that region 2 is relatively low. Okay, so that of course you can infer that either mathematically or from your physical intuition. You can figure out which of them is higher and lower and so on. Okay, so let us solve one quick problem using this equation and then we'll move on. Okay, consider a leaky confined aquifer 4.5 meters per day horizontal K overlain by an aquitard with 0.052 meters per day vertical K. Okay, if the flow in the aquitard is in the downward direction and makes an angle of 5 degrees with the vertical, determine the angle made by the flow in the confined aquifer. Okay, so it's a simple case of um, um, just writing out that equation K1 by K2 equal to tan theta 1 by tan theta 2. K1 and K2 are given. K1 is, what is it, 0.052 and K2 is 4.5 meters per day. And the angle made in the aquitard is 5 degrees, which is as close to, you know, a 90-degree angle with respect to the uh, horizontal, let's say, right? So you just solve this equation, you get theta 2 equal to 82.5 degrees, which means it is almost wanting to flow in a horizontal direction. The general rule is in an aquitard, the flow direction will be vertical. In an aquifer, the flow direction will be horizontal. Okay, this is some kind of a general rule that you can apply at any location anywhere in the world. If you see an aquifer, predominantly the flow will be parallel to the layering, to the layer, okay, or going in a horizontal direction, right? And in an aquitard, predominantly the flow will be vertical. Okay, so that's the general rule of thumb that you can follow. Okay, any questions before we move on? All right. Okay, so final little lesson on flow nets. Now we'll talk about it in the context of anisotropic aquifers. I'm going to go through this quickly. There's a very nice YouTube video available which explains this in more detail if you're interested. I'll send you the link to that, and that has a little bit more detail than what I'm going to do today. But you can just follow that. It'll tell you all that you need to know. Okay, so let us say I have an earthen dam, uh, right? So what I have here is an earthen dam, and I have two water bodies on either side of the dam. There's a headwater and a tailwater, and so there's going to be flow across this earthen dam. So let's say the water table will do something like this. Okay, some approximate shape you'll have. But if I try to draw a flow net for this particular setup, what happens is that because the hydraulic conductivity, now I'm conceptualizing this as a two-dimensional system. It's in the XZ plane, and we are assuming that this dam, let us say, is very long in the y direction. So there's no difference. Wherever you cut a section, the flow will look the same, right? So therefore, there is no flow happening in the y direction. The flow is happening only in the x and z directions. Okay, so you can analyze this problem as a 2D problem rather than a 3D problem, because in the third dimension, which is the y direction, there is no there's not much difference at any cross section. Every cross section in the y direction is going to be the same. Okay, so it's a 2D problem. Now what happens is, in this particular case, I've drawn two vectors denoting the magnitude of kx and kz, right? Now the vector in the x direction kx, I've drawn it to be longer than the vector in the z direction kz. Right? This is something very typical. Uh, Typically, the horizontal hydraulic conductivity in an earthen dam will be much greater than the horizontal, the vertical conductivity kz. Why is that? Why will kx be greater than kz? I've drawn it like that. Can anybody explain why that will be the case? Okay, the reason typically this happens is because these earthen dams are constructed in layers. You will have a layer of soil put, and then it will be compacted nicely. Okay, and then the next layer of soil will be placed on top of that, and then compacted nicely. Right. So the compaction is very, very tight in the z direction. Okay, and so therefore the soil is very tightly compressed in the z direction. So it would prefer to flow along those compacted layers rather than across the compacted layers, right? So there's a preferential direction of flow. Water will prefer to flow in the horizontal direction as compared to the vertical direction because of this very strong compaction. That compaction effort kind of it's done in layers. So therefore you have this strong preferential direction for flow. So therefore the hydraulic conductivity in the x direction is generally speaking larger in magnitude, probably 10 times larger than the hydraulic conductivity in this z direction. Okay, now when that happens, this becomes an example of an anisotropic aquifer. In an anisotropic aquifer, the equipotential lines and the flow lines, I've tried to draw that over here, they will not be orthogonal to each other. Okay, so the equipotential lines and the flow lines will not be orthogonal to each other. Now that makes the analysis of the problem relatively more difficult. Okay, so typically what is done is we take this anisotropic aquifer, which has a preferential direction of flow in the x direction, and we transform this into a system where you convert this into an isotropic system and then solve for the flow net. For the isotropic system, the flow net analysis is really straightforward. It's a simple Laplace equation. You can solve it, and you get the flow nets. Then you can again transform the system back to the anisotropic form, and then you'll be able to get the actual flow nets, right? So the analysis is much more easier for an isotropic aquifer. So what is done is we take this anisotropic aquifer and transform it into a new system in which the hydraulic conductivity in both directions is equal. Okay, so I'll not get into the math of it. I'll share this YouTube video with you, very nicely created, about 10 minutes long or so, and it explains this beautifully. So there's no need for me to again repeat whatever is said in that video. I'll just share that video with you. It'll absolutely clear any confusion that you might have. Okay, so the transform system will look something like this. Okay, it won't be the same length L in the x direction. It will be a smaller length L, and if you assume that kx is about 10 times kz, right? So this anisotropy ratio is square root of kz divided by kx. I won't get into why it's square root and so on and so forth. That video that I'm going to share will explain all of those things very nicely.
Sir,
Yes, is there a question?
that means we transform from the system from rectangular to square section. Rectangular to square section.
No, what do you mean by rectangular?
The transformation from rectangular section to square section.
Okay, so
Then
you
the
can think of it that way. Yeah, you can think of it that way, that because kx is longer than kz, so you can think of it as a transformation from a square to a rectangle. Okay, sure. Okay, so the ratio that you get is the anisotropy ratio. It's the square root of kz by kx, and if kx is about 10 times kz, which means the hydraulic conductivity in the x direction is 10 times more than the hydraulic conductivity in the z direction, so then that ratio becomes square root of kz by 10 times square root of kz. So that's about 1 by 3 or so, so which comes to 0.33, right? So the original aquifer, the original dam has got a length of L. Okay, and we transform that into a new system where the length is now 0.33 times L. Okay, now this is assuming that kx is 10 times kz. You can of course have another value, you'll get a slightly different answer. Okay, but and once you transform it into this new system, now the equipotential lines and the flow lines will be orthogonal to each other, and then you are able to solve the flow net using this new transform system. Once you finish solving it in this new transform system, you again apply that anisotropy ratio back to this and expand your flow net out, and you will get the actual flow net. Okay, so that's what is typically done in the case of the anisotropic aquifer. Now when you modify the system, you also have to modify the hydraulic conductivity of this particular medium, and that effective hydraulic conductivity is given by K prime. It's no longer Kx and Kz. It's this new effective hydraulic conductivity K prime, which is square root of Kx into Kz. Again, that's sometimes referred to as the geometric mean of these two hydraulic conductivities. Again, I'll share this YouTube video with you, which explains this in very nice detail with some nice cool graphics. I'll not be able to recreate those graphics here. So when it's available online, there's no point in recreating it. So I'll just share that YouTube video with you, and that should be able to help you understand what exactly is happening in this anisotropic aquifer. Okay. So basically the idea is to transform the system into a new system where the Laplace equation can directly be applied, and it helps you to solve the problem in a straightforward manner. And then you just go back and retransform the system back to the original dimensions, and everything gets transformed back to the original shape, and then you're done. Okay. With that, we are done with this topic of flow nets. Okay, so I'm going to move on to the next topic. So let me start sharing that screen. Just hold on. Okay. So now we'll spend about the next 15-20 minutes on this. We're going to talk about the different environmental influences on groundwater levels. Now, we will try to cover as many different environmental influences as possible, but we might not be able to do every single one. But we'll try. The major ones will probably be covered in this lecture. Okay. So broadly speaking, there are different types of environmental influences that can have an impact on groundwater levels. Now, I can divide them into things like seasonal variations, which are strongly governed by the seasonality of irrigation schedules and so on, right? So, for example, if you look at India, depending on which part of India you're in, from around end of May, early June, up to September or October is when you receive the predominant rainfall across the whole of India happens between end of May to mid of October or so on. Okay, and in this duration, a lot of cultivation happens, and so therefore there is both rainfall coming in, which brings in recharge, and then there's also irrigation pumping, which is following some kind of a seasonal cycle. So every year during the same time, there's a lot of pumping that is going to happen. Also, recharge is also happening, and so on and so forth. Right now, if you go to the month of October, November, December, if you are in South India, Andhra, Telangana, Tamil Nadu, Karnataka, and so on, here also you have the retreating monsoon, the northeast monsoon coming in at that time, and therefore, again, because a lot of cultivation is happening during this time, which spills over again into January, February, up to around end of March is when most of the cultivation is done, and predominantly people will stop. If you have two crops, the first crop is in June and the second crop is in, let's say, November or so. You harvest it in March, maybe early April, and then April, May, most likely most farmers don't do any cultivation. They don't cultivate a third crop because it's peak summer and they don't have the water because the rainfall is not going to happen in April and May. So depending on whether the farmer has a bore well or not, the farmer may choose to pump or not pump. Again, so many factors go into it, but there is a seasonality to it. So every year you will find the same kind of pumping schedules and the rainfall schedules coming through year after year, and this has an impact on the groundwater levels. But this is some kind of a seasonal cycle, right? So that's a long-term trend, right? And you can clearly observe this every June, July, August, and so on, and then every March, April, May, you will notice that there is less irrigation pumping, and so on and so forth. Okay, so this is a seasonal cycle. Now, this is specific to India. If you're living in a different part of the world where there's a different schedule of the monsoon and the rainfall and so on, the schedule will be different, of course, right? So we are talking about the general idea of how these kind of seasonal variations can impact groundwater levels, right? So this is at a slightly longer scale. Now there are also other short-term variations like diurnal variations. Anybody knows what diurnal means? Diurnal. What does it mean? It's the variation that happens within a day. Sorry.
Diurnal variation. Temperature will be rise in the daytime and low in the night
Correct.
time, and summer also
Correct.
temperature is
Correct.
rise.
Yeah. So now I have
Yes, sir.
listed, now in this context, we are talking in the context of groundwater, right? So, for example, if there's municipal water supply, the municipal water supply typically happens early in the morning, right? So they'll start the municipal water supply pumping will start early in the morning because that is when majority of the water demand is felt by the entire city, right? Between around 5:30 a.m. till 9:30 or so is the peak demand. Okay, so the city supplies water at that time, which means if the city has some wells, they will pump the water, get it treated, and have it ready, and they will supply it. Again in the evening, between maybe 4 or 5 till about nine in the night, is when again there will be a demand. Peak demand happens in these two, the morning and the evening. So at those times, to cater to the requirements of the city has to pump out water, treat it, have it ready, uh, uh, and then distributed through the pumping network or the pipe network in the city, right? So that's a diurnal variation. So every day there will be two peaks in demands, which means there will be a spike in the pumping. It will not be continuous pumping all the time. They'll pump out the water, treat it, send it out, and then for the next peak again there'll be some pumping happening, and again treatment, and then again supply throughout the city. So that is a some kind of a diurnal variation that happens on a daily basis. Now this is when it comes to municipal water supply wells. When it comes to industrial wells, they may have some kind of weekly variations, right? Weekly variations because the industry will typically run from Monday to Friday, or maybe Saturday in some cases, and then Saturday, Sunday, the pumping kind of goes down, and then again Monday when the industry resumes operations, it continues, and so on. And of course, depending on the nature of the industry, some industries will have demand at different cycles. So if you're manufacturing a car, for example, um, the water requirement of that industry is very different from a food processing industry, which probably requires water throughout this entire cycle of the production, and so on and so forth, right? So it will vary from industry to industry, but generally speaking, industries will have an off day, a day or two in the week, and then the rest of the week it's there's a need, and then for one day or a couple of days in the week, the demand is shut off. So there's a weekly variation. So these are the, relatively speaking, the short-term variations that happen in the and these impact the groundwater levels, right? Because industries might typically be pumping a significant amount of water. The municipal water supply wells are also supplying a significant amount of water. Yeah, Shantanu,
Yes, sir. Sir, the
go ahead. You raised
maximum
your hand.
maximum water demand is the demand of the maximum hourly demand. Na? In that day,
Okay.
we have to design for
Okay.
the system like this.
Correct. What I'm talking about here is the impact on groundwater levels. So when there is a peak demand, to support that demand, you will have to pump out a certain quantum of water. Now it depends on what that demand is and so on and so forth. But when you pump out that water, it is going to have an impact on the groundwater levels in the nearby regions, right? Now the demand is not going to continue for the entire day. You might have a peak demand at a certain time. To cater to that, you pump out the water, and then after that you stop. So the water levels will begin to recover again. And then the same peak demand will happen again the next day, 24 hours later or 12 hours later, whatever it is. So I pump, I satisfy the demand, and then there's no pumping. Again, 12 hours later or 24 hours later, again I have to pump to satisfy the demand, and again I shut off the well because the demand has been met. Right? So that's what I mean by these diurnal variations. Right? It could also be a daily variation. It need not be twice a day. Depending on the city, depending on the demand, you might have twice a day, you might have once a day. Okay? But basically, these are short term
Yes, sir.
variations. Now, in the context of what I spoke about earlier, which is seasonal variation, which has got a much longer time cycle, these are relatively speaking short term. So that is all I'm trying to say in this context. Okay. All right. So now moving on. Now, stream flows can also have an impact on groundwater levels. Now, uh, I don't know if you have heard these two phrases that I'm going to mention: a gaining stream or a losing stream. Are you familiar with these two concepts? Anybody has heard about it? Fairly obvious, right?
No, sir.
A gaining stream is one which gains water from the aquifer. A losing stream is a stream that provides water to the aquifer. Okay, so in that sense, streams are either gaining or losing. Gaining means it's gaining water from the aquifer. Losing means it's losing water to the aquifer. That's all. Okay, so these kinds of streams, if there is a gaining stream, right, the aquifer is actually losing water to it, which means the water levels in the neighborhood of this gaining stream will get definitely impacted by the presence of such a stream. And the other case also is possible. If the stream is providing water, then that might also help enhance the water levels in the surrounding regions near the stream. Okay, there is also what is referred to as bank storage, right? So what happens is I have a river. Okay, let me try to draw a cross section. Okay, let's say I have a oops, sorry. This is my river, and this is the water level in the river. And in the surrounding area, I have the water table that looks something like this. Okay. Now a rainfall event happens, and the water level in the river suddenly rises up to here. Okay, the original water level in the river was here, and in a short time, the water level in the river rises up dramatically to the extent that it has now changed the gradient between the river and the aquifer. Right, prior to the prior to the flood, prior to this water level being raised, the the gradient was from the aquifer to the stream. Right, so the stream was actually receiving water from the aquifer. Right now, because this flood has happened in a very quick time, right? Groundwater levels don't respond so quickly, right? Groundwater levels are relatively slow to respond. They respond relatively slowly. Okay. Now, what happens? Immediately, the gradient is reversed, so the water will start infiltrating into the aquifer, right? So water will start infiltrating into the aquifer, and which raises the water level in the banks right adjacent to the river. Do you agree with the characterization that I've done? Right? Initially, the water level in the river is low. The aquifer is at a slightly higher level, so it's supplying water to the river. Suddenly, in a short time, let's say 1 day or 2 days, due to a rainfall event, the water level in the river suddenly goes up, and it changes the direction of the gradient between the river and the aquifer and starts to supply water to the aquifer. to the banks along the river. Okay. Now what has happened is I have actually changed the gradient, direction of the gradient, and I have stored some water in the banks of the aquifer. But this flood, right? The water level in the river is not going to remain so high for a long time, right? Usually the rain stops, the flood goes down, and it again starts to come down. So the water level again, maybe it comes down to somewhere over here, let's say. Now what has happened is, because of that storage of water in the process, when the water level went up, some of the water was stored in the banks. Now that water again starts to slowly pour out, but not everything can come back into the river, right? So some bank storage is created in the region just adjacent to the river. On both sides of the river, you will have this additional bank storage, which is raising the water level locally, very adjacent or very close to the stream. You have some additional storage capacity being created in the along the banks of the river on both sides of the river. Okay, so now that is referred to as bank storage. Okay, now this process is not perfectly reversible, right? Water level goes up in the river, it goes, the gradient changes, and some water is stored in the aquifer. Now the water level in the river goes down. Not all the water that went out into the banks is going to come back into the river, right? It's not a perfectly elastic process, if you can call it that, right? So there will be some storage of water along the banks of the river, which is created due to this occurrence of the flood, and then the lowering of the water levels during the recession of the flood. So the flood levels go up and then it starts to come down again, and that creates this additional bank storage along the banks of the river. Okay, is that all right? Okay, let's move on. Then there's evapotranspiration. Now, how could evapotranspiration impact groundwater levels? We have to keep one thing in mind: evapotranspiration can play a role in mediating or changing groundwater levels only if the water table is relatively close to the land surface. If the water table is pretty far from the land surface, generally speaking, evapotranspiration does not play a major role in those situations. But if the water table is within, let's say, 2 to 3 meters from the land surface, right? Because most plants, their roots cannot go more than 2, maybe 3 meters, right? 1 to 2 meters is the general depth that roots of plants can penetrate up to 2 meters, right? About 6 feet, 6.5 feet. Once you go deeper than that, of course, there are some exceptional plants which are able to go much deeper in search of water, but those are not commonly seen. Those are very special plants, maybe seen in the desert somewhere or whatever it is, right? Generally speaking, the what is called the root zone happens in the top 2 to, let's say, 3 meters max. Okay, 3 meters of the land surface, top 3 meters from the land surface, is what is referred to as the root zone. Now, if the water table happens to be in this root zone, then evapotranspiration can actually play a major role in changing the water level there. Okay, suppose I have a lot of plants in a particular region, and if the water table is very close to the land surface, then those plants can suck up that water through the capillary action and use that to evapotrans as during transpiration, and then that allows the plants to grow. The more the plant grows, the more the water it is able to extract um, from the soil, and therefore the water level in those regions will start to fall, right? And of course, then there's a natural balance to it, right? So if the water table is too high, the plants can grow really tall. The more the plant grows taller, the less water there is. So then the water table starts to fall, and if it falls below 3 meters, then that limits the plant from growing any further. So there's this balance between how high a plant can grow versus how low the water table can go, and so on, right? And then if it rains, again it raises the water table, again it sets up some growth, and so on and so forth, right? So this is only predominantly observed when the water table is close to the land surface. I said 1 to 2 meters here. Absolute maximum I would think of is 2.53 meters. I can't imagine evapotranspiration playing a role in groundwater levels if it is more than 3 meters deep. Okay. Now, if you look at data across India, most regions across India, apart from maybe northeastern India, the water tables are typically 10 feet or below the land surface, right? 10 feet is supposed to be good, right? But there are very few places in India where you consistently have water table within the top 10 feet, right? So it's not really a major concern in most parts of India. But anyway, so that's this is just for you to keep in mind. Okay. All right. Rainfall. Now, this is, I mean, I don't think I have to say how rainfall can impact groundwater levels. More rainfall happening over a reasonably long duration will generally have the impact of raising groundwater levels, right? But this is not true if the rainfall happens in a very short duration. Then most of the rainfall will become runoff. But if the rainfall is distributed over a sufficiently long duration of time, then the soil will get a chance to absorb that water, and naturally that will result in the raising of water levels due to these environmental influences. Okay, so that's the role of rainfall. Okay, just conceptual pictures I'm going to show you from some very well established articles that are available online. This Barlow et al. Is a very classic kind of report by USGS, the United States Geological Survey. You can check it out. They just give some nice cartoons or nice conceptual diagrams which explain all of these different concepts, the gaining stream versus the losing stream. There are also what are called disconnected streams, right? And then dried up streams and so on and so forth. Okay. So anyway, so I strongly refer this particular report that's given at the bottom. The source is given at the bottom. Please take a look at that report. It is by far the most comprehensive report that talks about the connection between stream flow and pumping in the aquifers. Okay, so you can spend a lot of time reading that report and understanding a lot of different concepts uh, in this context. Okay, what time is it? Oh, we are over time. So I will stop with that. Yes. Is there a question?
Sir.
No question?
No, sir. People
Okay.
are waiting.
Oh, okay. All right. Thank you very much. See you guys on Friday. All right. Take care. Bye bye.